Okay, we're going on to part three, boiling. Let me dismiss my image and begin. Boiling is the rapid evaporation from beneath the surface of a liquid. Um, you can see here that they're showing the forces from air pressure, and that gets transmitted to the pressure in the water. And there's pressure for the bubble, that it's the outward pressure. But if the pressure here is greater than that of the bubble, the bubble will collapse. Um, Rapid evaporation beneath the surface forms vapor bubbles. Bubbles rise to the surface. However, if the vapor pressure in the bubble is less than the surrounding pressure, then the bubble collapses. Hence, bubbles don't form at temperatures below boiling point. The vapor pressure is insufficient. Now, if you were to have a um, pressure cooker, the tight lid of a pressure cooker holds pressurized water vapor against the water surface, which inhibits boiling. Therefore, the water reaches temperatures higher than 100 degrees C. Um, okay, uh, Boiling water at 100 degrees C is in thermal equilibrium. Boiling water is being cooled as fast as it is being warmed. In this sense, boiling is a cooling process. So you have the heat going into the pot, warming the water, but as the energy leaves the water, it's cooling. Okay, boiling point depends on pressure. Buildup of vapor pressure inside a pressure cooker prevents boiling, thus resulting in a higher temperature that cooks the food. Boiling point lowers with lower atmospheric pressure. Water boils at 95 degrees C in Denver, Colorado, um, which is a high altitude, rather than at 100 degrees C at sea level. And that's why if you look at a box of macaroni or something like that, they have high altitude directions where you have to boil it for a longer period of time. Um, okay, and here's a demonstration of a cooling effect of evaporation and boiling. So if you put room temperature water in a vacuum and you draw uh, draw out the air using a vacuum pump, you will the water will boil and it'll even freeze. And there the fellow is holding some uh, ice. It's ice that was frozen using this method at the um, museum um, that they're that this picture is taken at. And it's also how they get freeze dried coffee. They vacuum it and the water boils off, and now you're left with the crystals of coffee. Okay, the process of boiling cools the water being boiled, depends on atmospheric pressure, and is a change of phase below the water surface. Well, the answer is all of these, all of the above. Okay, melting occurs when a substance changes phase from a solid to a liquid. It's the opposite of freezing. When heat is supplied to a solid, added vibration breaks molecules loose from the structure and melting occurs. It occurs when a substance changes phase from a liquid to a solid. Freezing occurs when a substance changes phase from a liquid to a solid. It's the opposite of melting. When energy is continually removed from a liquid, molecular motion decreases until the forces of attraction bind them together and formation of ice occurs. Okay, they during the winter they pour salt. In some cities, they pour salt onto the roads. Why is that? Well, in a mixture of ice and liquid water at 0 degrees, the number of molecules entering the solid phase is equal to the number entering the liquid phase. You can see this is a conceptual drawing, but you can see the three black lines. Uh, they're they're leaving, and the three blue lines they're entering. Um, and so this is freezing at normal with normal water. Now, if you were to add uh, salt, you can see that it it reduces the amount of lines. You know, you have lines that are going out from the frozen side, and only one coming in. So it lowers the the uh, the freezing temperature. That's why they pour salt on roads. Okay, regelation. Um, it, it this is nothing I'm going to test you on. It's just something for you to know. If you were to take a copper wire with suspended weights, it would gradually pass through the ice block without cutting it in half. In other words, at the top, it starts melting the ice, and as the copper wire cuts through the ice, the the melted part above it refreezes, so that wire will go through the ice, and by the time it reaches the bottom, it'll be a solid block of ice. Now, you need a good conductor. This won't work with string. You know, string would be a good insulator. So you need a good conductor. That's why you would use a copper wire. And that's the end of this section.